A pleasure to see you conducting this event so efficiently, and your team and the support we got from seniors. I'm thankful to Dr. Rao for his never-ending support to all the events that we have been organized, that like we're organizing in India. And so I will go ahead with the title of the talk that we delivered during this session. The first talk will be delivered by will be delivered by Mr. Lars Jacob-Ford. The title of the talk is Antenna Testing Using Far Field and Near Field Techniques, and which will be followed by another talk by Lucia Scialacqua. The title of the talk will be Synergic Use of Antenna Measurements and Numerical Simulation in Antenna Placement Scenarios. So I will introduce the first speaker. Thank you for joining in. Mr. Lars Jacob-Ford, and Mr. Lars Jacob-Ford has 30 years of experience in antenna design and measurement techniques. He received his Bachelor of Science from Aarhus Technicum, Denmark, and Master of Science in Electrical Engineering from California Institute of Technology, USA in 1990. He was with the European Space Agency, STEC, and successfully designed communication and navigation antennas for the satellite industry. In 2001, he joined Microvision Group and founded the Italian branch office. He's currently the scientific director of the Microvision Group. He was a member of the UCAP Delegate Assembly and Working Group responsible on antenna measurements from 2009 to 2012. In UCAP, he was Conference Vice Chair in 2011 in Rome, and again in 2022 in Madrid. Industrial Chair in 2012, 2014, and 2017, a Technical Program Chair in 2016 and 2021. He is Vice Chair of the IEEE Antenna Standards Committee and contributed to the development of different standards on antennas and measurements since 2004. He is a board member of the European School of Antennas and technical responsible for the antenna measurement courses worldwide since 2006. He has been involved in the evolution of IEC standards and human exposure to electromagnetic fields since 2010. In 2016 and 2017, he led the Industry Initiatives Committee, a standing committee of the IEEE AP Society. He is an Edmund S. Gillespie Fellow of AMTA and a member of the AMTA Board of Directors. He received the Distinguished Achievement Award in 2017. In 2015, he contributed to the foundation of the AMTA Italian Node. He has authored or co-authored more than 300 journal and conference papers on antenna design and measurement topics and received the Best Technical Paper Award from AMTA in 2013. He has contributed to several book standards and patents. With this, may I request Mr. Lars to go ahead with this presentation. Thank you so much.
First of all, thank you very much for the invitation. And I will try to send a shorter bio for next time because it was probably a little bit too long. So I will try to remember this for next time.
Thank you.
Let's see. Are you able to see my presentation?
Yes, we can.
Okay. So I tried to put together something similar to what we saw in simulations on this kind on antenna measurement. So it's an introduction to how we can measure antennas using different techniques, both in far field and in near field. The way we are going to do this is that I'm going to talk for about 1 hour more or less, and then I'm going to hand over to Lucia that will then talk about an interesting topic that will link what I talked about together with what was talked about from Dr. Reddy. So I think it will be quite nice to bring everything together in the end. So I need to see if I can get it to work. So this is the outline of the talk. First, I'm going to introduce you to antenna measurements. I saw there was one question about how to interpret a pattern, and it has to be said that in simulations, life is easy because you can measure or you can simulate the field values in a point, but in real life, when you're trying to do exactly the same thing, it's a little bit more difficult. So I will give you an introduction to antenna measurement, and also try to include a little bit about OTA measurements, which is over the air, because I know for many of you, especially the younger ones, that this is going to be something that you will see quite a lot in the future. Then I will talk a little bit about the various near field and far field measurement solutions we have, the most standard ones we have. And then I'm going to show a little bit of a overview of some measurements and what we can actually learn from a measurement campaign. So keeping to the space scenario, it's going to be a payload, so a satellite, a navigation satellite, and also a navigation antenna that we will look at. And then including, so that's more about near field techniques. And then for far field techniques, I'm going to talk a little bit about the plane wave generators, which are compact antenna test ranges, and also the newer solutions that are based on arrays. So let's talk about introduction to antenna measurements. So when we try to do antenna measurements, we are mainly interested in characteristics in the far field. And this is maybe a little bit of a paradox, because a lot of the communication we are doing today actually happens in near field. But it is convenient because it is a standard way of being able to communicate two measurements and still get the same results. So it is quite nice as a standard situation for evaluation and comparison. So normally when we try to measure an antenna, as you can see here, so it's pattern in 3D space, we have to do this by using a probe. So we have to use another antenna, and what we are really measuring is the coupling between these two. We cannot, as Dr. Reddy, just calculate the field value in a point, but we have to use a probe, or a probe if it's a near field technique, and a range antenna if it is a far field technique, to get a feeling for the coupling in 3D space between, in this case, the probe and the antenna I'm trying to measure, and then move either the probe or the antenna on the test in 3D space, so that we can evaluate what is the coupling between these two in all of 3D space. And that will give us an idea about how the antenna is radiating field in 3D space. So a typical way to impose such a system, here we have the antenna we try to measure, and again the probe, could be to put everything inside an anechoic chamber so that we are not disturbed by radiation from the outside, and also that the radiation that we send out in space is not, let's say, disturbing what we are doing. So we have absorber lining on all the walls. The probe, in this case, would be fixed, and we could put our antenna that we want to test on a positioner, which will then rotate in 3D space, so that we can record the actual coupling between the probe, or range antenna in this case, and the antenna that we are trying to measure. And that is a typical way that antennas are measured for almost 100 years. So if we ignore a little bit the fact that we know that there's such things as near field also, then we could simply apply what was developed by Mr. Friis. Harald Friis was actually a Danish scientist, and I'm also Danish, so it makes me quite proud that he made this contribution to antenna measurement. So what he says is that the S21 between a probe and an antenna we are trying to measure is essentially the gain of these two antennas and a path loss. So what it really says is that energy radiated, electromagnetic energy radiated, is never lost, it's always conserved, and it is distributed over a surface that becomes larger and larger the more you increase the distance, so the density goes down, and that's included in this path loss that you have here. So clearly the S21 is the coupling between the power into the antenna on the test and the power coming out of the probe, or vice versa. What is also interesting to notice is that at very, very small distance of just one wavelength, the free space loss is already 22 dB. This is one of the things we need to worry about when we measure antennas, is that very rapidly we're going to have some attenuation. It's not the same as having two circuits connected together. When you have two antennas and we have free space propagation, we are going to have to deal with some losses. The simple way to measure antenna gain, which is to use what we call the gain substitution technique, is to first make a calibration of the system in which we use a reference antenna that has a known gain. By recording the S21 between the probe and the reference antenna, we can then do a second measurement, which will be the one in which we'll include the unknown antenna. In this case, it's a mobile device, but it could easily be a satellite. It's exactly the same procedure. And from these two measurements, we can then determine what is the gain of the unknown device here, simply from the measure at S21 in this case, and then a correction term that is a calibration factor that comes out of this calibration we have done on the system using a reference antenna. And also, if there's a difference in path loss between the two, we need to also calibrate for this. So this very simple way of calibrating our system is actually the basis for all the measurements that we can think of in near field and far field, and even including also OTA measurements. When you do your system calibration, which is quite important, you should use, and this is just a recommendation, it's not a requirement, you should try to use a reference antenna, in this case a dipole, that looks a lot like the antenna that you're trying to measure. That is just a recommendation, because in that way you are able to optimize also the coupling in the two measurements, and also the disturbance of the antenna in the system will be more or less the same, and therefore it's more likely that you will get a good measurement. But it's only a recommendation, it's not a requirement. What is important is that when we do this system calibration, so we take a reference antenna with a known gain, and we actually go ahead and calculate the system calibration factor for this system, what we really get from this is that any antenna that we place at the post of the reference antenna, the connector that we have in our probe or range antenna is going to be directly linked with this calibration factor to any power that comes in and out of the unknown antenna we put here. And this is quite important because it will allow us also to measure antennas that have their own power, for instance, mobile phones. But when we put it in the position here. As a matter of fact, most of the antennas that we are trying to measure are active, so they have their own, let's say, amplification. In some cases, for instance, in space and military, you will find that there is some kind of elaboration of the data, so you try to communicate with the military hardware, and it will try and communicate back to you, like a radar, for instance. Many of the base stations and all of our mobile phones generally do not allow us to attach a connector and try to measure radiation, but we actually need to communicate with the antenna that we are trying to measure in order to be able to characterize it. This is actually a very large part of the antenna cases that we need to measure. Of course, the antennas that are maybe used for space, for instance, generally has a connector. All the horn antennas that we've seen so in the previous presentation generally has a connector, and when we can connect it to the antenna we are trying to measure, then the kind of measurements that we are doing is let's say what we call a passive system testing, and this is maybe the most classical of all of them. And I'm going to talk mostly about this in this presentation, but I'm going to give you a little bit of indication also on the auto testing or the active system testing. So when we are dealing with devices that have amplification inside and maybe do not have direct access, like for instance a mobile phone, then we don't have a direct link. So we are doing the measurement in over-the-air setup, in which we try to, just like before, find out what is the spatial radiation in 3D space of this device without having the possibility to really connect to it, but only communicate to it over a distance. So what we need to acknowledge is that when we've done the system calibration that we did before, so putting a reference antenna in place of the antenna that we don't know and calibrating the systems, we actually have a relationship between the power in and out of this port here, exactly related to the power that is in and out coming of the unknown device here. So we can easily measure, even though we don't have a direct link to the antenna we are trying to measure here. So the real question is, are we going to do radiated testing? Well, then we have a connection, so we can use S parameters to establish the coupling between the unknown antenna and our probe. And in some cases, we do auto testing over the air. So after we've done a system calibration or gain calibration, then the probe becomes a virtual connectorized port of the device that we are trying to measure. But in both cases, we can do antenna measurements. We can establish the radiation in 3D space from our antenna or antenna system as we have here. Generally try to measure, well, the most common thing that we would like to measure is probably the pattern. So we would like to know something about the gain and the directivity. But when we start to go into, let's say, measurement of antenna systems, where we have an amplifier or other hardware integrated into the antenna, then we would also maybe like to look at things like how much power and what is the power density that is radiated by this device and so on. If we have a receiver in the system, well, then we will be looking at sensitivity, how sensitive is our receiver, and so on. Now, in these presentations, I don't have time to look at everything. For passive systems, we're going to look at gain and directivity in this presentation, and we are briefly going to look at power measurement for active devices, so OTA, and we're also going to look a little bit at the efficiency for passive systems. So if I wanted to measure, for instance, how much power I was able to generate in my mobile phone, which is my own device, as I said before, I will calibrate my system first. So my reference antenna, I know the gain of reference antenna, calibrate my system. Now I know that when I place my device here, I have a calibration coefficient that will give me a translation between the power I really receive here to what is the power radiated by this device here. So we get a direct measurement of the EIRP, which is the effective isotropic radiated power by this device at this position here. I can move my probe around in 3D space and get a mapping of how much power is actually radiated and the power density actually, how much is radiated in 3D space. And if I integrate this over the 3D space that I measured, then I get the total power. Just to illustrate, if I did this measurement with a network analyzer, so this is my unknown antenna and my probe, and I try to do the measurement with the network analyzer. So now I have a normalization because the network analyzer will tell me the ratio between the received power and the transmitted power. And I do my integration. What I really get is the efficiency of the antenna. Whereas if I use a spectrum analyzer or other power meter in this exact same measurement, and of course I need some kind of source, it's either integrated in the antenna or not, then what I really will be measuring at this point with my probe or coming out of the connectors here is really the power density, so the isotropic power density at the antenna port. And when I integrate that in 3D space, what I get is the total radiated power of my antenna. So that is really the difference between an OTA measurement, in which we are interested in some power characteristics, and what we could call a normal measurement, in which we are able to connect with the antenna, and we could, in this case, for instance, get the directivity or also the gain or the pattern of the antenna from this measurement, because we have a direct link. Unfortunately, what happens is that for each antenna we have what we could call the near field effect. So if we took two antennas and we mount them front to front, very, very close to each other, well, according to Fries, theoretically we should have the gain of both antennas, but that's not physically possible. So the conclusion is that the freeze transmission formula is only valid when we are really in the far field. And when are we really in the far field? Well, if we have a small antenna, and this is similar to a mobile phone, and then the pattern we are radiating are basically potato type. And if you look at the different patterns in different colors on the screen, at different distances, you can see that already at half a meter distance from this antenna, so more or less here, the pattern does not change. If you go to 2 meters, 5 meters, and so on, you are already from a small antenna, more or less in the far field. If you take a larger antenna, in this case an 8x1 array, and you do exactly the same thing, you plot the pattern, that you measure different distances, you can see that at 1 meter distance, the pattern does not at all look like the far field pattern that has the nulls, the side lobes, and so on. So there's clearly a big difference in where is the distance in which you measure the antenna and the true far field pattern. So what we are seeing is that from a certain distance from our probe, we radiate a spherical wavefront. That spherical wavefront, when we project it onto the antenna we are trying to measure, we're going to make an error, and it is generally a phase error, not as much a amplitude error. And one of the rule of thumbs on how to deal with where is the far field is to say that when this error becomes less than 22.5 degrees, which happen at this distance here, so 2 times the maximum diameter of the antenna we are trying to measure squared divided by lambda, then this error is within or less than 22.5 degrees. Unfortunately, there's no real guarantee that your measurement is going to be good at this distance, as I will show you here. So if we take the 8x1 array from before, and then you recognize that the different patterns, as you can see here, the one at 40 lambda, which would be the far field distance, we can then go and look at the error in terms of distance. Well, at the far field distance, the error on gain would be 0.4 dB. And the error on the first side lobes, as you can see, it suffers a lot. The side lobes, they're not really truly defined at these distances. Has a 2.5 dB error. That can be acceptable in some applications, but in other applications, it's clearly not acceptable to have such errors when you are trying to make very accurate antennas. Then you will not be happy with such a result. So the far field distance by the classical formula will give you an indication, but it's not a guarantee that you're going to be able to make good measurements. So what is the far field distance for different types of devices? So from the small chip to the phone, the tablet, the BTS antenna, a car or a satellite, you will see that with frequency going up from 70 megahertz to 60 gigahertz, the far field distance, according to the formula we derived before, becomes very, very big. In particular, when you have big objects like car, satellite, chips, and so on, we are talking about many, many meters and kilometers of distance in order to be in the far field. And that's clearly a disadvantage because it's expensive to make a system that are able to measure at so distances. The other thing that we have to be worried about is that at such distances, the free space loss in some cases may also be very high. So we may not be able to get a good S21 when we try to measure the coupling between the antenna that we're trying to measure on the structure and our probe. And that's also a problem with typical far field systems. So let's look at what we have in terms of near field and far field measurement solutions, because if we stop here, it looks rather dark, especially if we have big objects to measure, but there are solutions. So on the left here, you can see the direct far field range in which you have the antenna you're trying to measure and your probe at a certain distance, and you try to increase the distance between them. And when you are at a sufficiently large distance, you are in the far field, and you can then measure directly the far field pattern of the unknown antenna here. Another way of dealing with this is to use plane wave generators. And in this case, for instance, a plane wave generator could be a compact antenna test range, or CATR. Now, the We will talk a lot more about this later in the presentation, but the compact antenna test range, what it does is that it takes the range antenna, will radiate a spherical wavefront, and the reflector is going to turn that spherical wavefront into a plane wave. And when we are in the plane wave condition, we are essentially in the far field. Clearly, we are not in the far field of the reflector, but we are able to synthesize a far field condition in a much more compact space, and that's why the system is called a compact antenna test range. And what really happens is that the reflector does an analog plane wave filtering of the field, or either from the antenna or from the feed, and make a near field to far field transform for us, so that we can measure at much less distances the performance of the antenna in far field. We can do similar thing in a near field range, in this case illustrated by a spherical near field range, in which instead of having a reflector to do the sampling for us, we do an analog sampling on a surface around the antenna, and then we need to digitally take the amplitude and phase information around the antenna and do a near field to far field transformation, and that way we get to the far field. So let's talk a little bit more about these solutions here. So near field first. So the near field transformation is really a consequence of the Huygens principle, as you can see in the upper right corner here, because we have the antenna under test. We have a probe in certain positions, and we can move it around the antenna and record the amplitude and phase at a certain distance. Then we can ask these on this surface. We can then say, well, that is the field values at this surface, and we can have them re-radiated in the field, the same value as we just measured here, and that's going to generate our far field. In order to be able to do this, we need to measure the tangential components at our measurement surface here, and we only need to really measure the tangential field information. This is illustrated down here. So if we have an antenna, as we had before here, and we have a surface, we use the tangential field components to generate the far field, as you can see here. And we also use, for instance, all components, or we use all components, so not only E field, but also H field. The only difference between these two solutions, this is much more complicated because you need to measure all field components, or also the magnetic field. This is simpler because you're only measuring the tangential components and only of the electrical field. They give exactly the same far field if you take the difference between the two. The only difference is that in the case of the tangential components, you don't really know what it generates in here, but you don't care, because when you do the near field to far field transformation, you are interested in what is radiated outside your measurement surface and not what is radiated inside. So we can actually do this rather easily, and we can do this on any scanned geometry. This Huygens principle is valid for any scanned geometry, but the most common geometries that we use for scan are spherical, cylindrical, or planar. This will be, I will show you this in a minute. So in order to make it even more efficient, because the Huygens principle will tell you need to sample at lambda over 2, but we can actually get around that a little bit easier if we make the expansion using a set of orthogonal basis functions. So I'm trying to simplify near field measurement theory to the maximum. And if you really want to know the inner workings of near field measurements, then you have to go and read some of the references I'm going to list in the end. But very, very simplified, what we are doing when we make a near field measurement is that we measure the tangential field at a certain distance r. We then expand this field in a set of basis functions that could be, generally it's spherical waves or planar waves or cylindrical waves at that same distance r. In that, we calculate the spectrums. That are the coefficients that will exactly reproduce the field we measured using these basis functions. Then, since these basis functions are known functions with a analytical formula, we can propagate that r from the measurement distance to infinity. And when we do that and we apply the same spectrum as we did in the near field, we get the far field. And this is the underlying principle in all near field to far field expansions independent of the or whether you're using spherical waves or other expansion means, you basically expand the near field using basis functions, and then you propagate them to infinity, and that way you get the far field of the antenna that you're trying to measure. Now, for spherical near field systems, the expansion looks like this, in which you need to determine the coefficients of the spherical waves at the distance r in which you are measuring the tangential fields. You could do that as a linear system, but the most important or the most accurate way to do that and fast is to use FFT. You can make this equation a little bit more complicated and take into account also the effect of the probe, which is quite important because, as I said in the beginning, if you're doing numerical simulations, you can calculate the field in a point. But when you do an actual coupling measurement, an S21 measurement between your probe or range antenna and the unknown antenna that you're trying to measure, you're really measuring the coupling between the two. And in order to get rid of your probe impact, you can also include this in the equation when you do the inversion and calculate the coefficient that you and calculate the far field of the antenna. So here's a view of the different spherical modes, and for the most basic modes, and then becomes more and more complex, you can see more and more variation in the spherical mode spectrum. So examples of basic functions that can be used are, of course, plane waves for planar measurements, spherical waves for spherical measurement like this one here, or cylindrical wave functions. But you could also, if you have, for all of these field geometries, you can use equivalent currents. This is one of the things that Lucia is going to talk about a lot more later, but very simplified. If I am measuring an antenna like this, I can define an equivalent surface in which I have a little triangular currents, and by direct inversion of my measured field in the triangulars, I can determine what are the equivalent sources, the equivalent electric and magnetic fields radiating exactly the far field or the near field that I measured, and this is one way of expanding, for instance, a measurement. In spherical, for instance, the number of modes that I need to be able to expand the near field that I measured actually depends on the maximum dimension of my antenna. So the maximum dimension of my antenna will tell me how many modes do I need to include, so the N and the M, in my mode spectrum in order to be able to measure correctly the radiation from this antenna. So going a little bit back again to far field measurement solutions, the antenna test range we talked about before can be very big. Sometimes the reflectors are tenths of a meter. This is the size of a person. So here you would have the feed illuminating the reflector. This is a single reflector system. And here you would put the antenna on the test. If you want to know more about this, a very good place to go and look at is this draft we are preparing right now for the IEEE standard 149, in which we are going to talk quite a lot about the compact antenna test range, as you can see. The same also goes for near field measurements systems like the one here. This is a planar system. It can also be used as spherical. If you go to the IEEE recommended practice, standard 1720, and again, we are making an update on this. That will be ready in 2023. You will learn a lot more about these measurement that I only introduced you to very, very simply. So different ways of applying near field antenna measurement. The spherical scenario is when you have a fixed probe or antenna on a tower, like the one you can see here. This is actually the antenna. This is a tower that can move as we did before in azimuth and elevation. So you get all couplings between the probe and the antenna on the test. Spherical field are generally for small to medium antennas. When the antennas get very big, then the sampling requirement becomes a little bit tedious, and it's also difficult to move a large antenna. Then you will generally go to the planar solution, in which you move a probe on a planar surface in front of the antenna you're trying to measure. And that's illustrated also here in the STEC hertz range, in which you have a tower, same tower here, that can be moved in the X version, X direction here, as you can see here. And you can map the field radiated by this antenna here. And that's generally used for medium to large antennas. So there are different measurement solutions, mostly adapted for different scenarios of measurement, but there's really not a fixed formula for what kind of system you should use for any measurement, but there are some indications, and these are the ones I'm showing you now. A classical planar near-field measurement, for instance, of this satellite here, we're going to see that in a minute. We will move the probe on a surface and try to sample at least with lambda/2 sampling in front of the satellite, as you can see here. And this field we will then simply treat by Fourier transform, an FFT, to calculate the far field radiated by the satellite, as you can see here. In terms of spherical waves, exactly the same setup, actually. We had the probe and we had the satellite, but now the satellite is moving in azimuth and in elevation around these two axes. There, the sampling is lambda/2 on your measurement, not on your measurement sphere, which is at the probe, but the projected minimum sphere around the antenna you're trying to measure. You need lambda/2 spacing. So you don't need as many points in spherical as you do in planar. The sampling step and the probe distance can be rather high as long as the projected spacing on the minimum sphere around the antenna here is lambda/2. In the classical systems, spherical, cylindrical, and planar are rather slow, we have to admit, because it's they require that you move your probe or your antenna on the test in various mechanical movements. A faster way to do this, and we will see that also later in the presentation here, is to use a multi-probe system. So use more probes. For instance, instead of having the movement in elevation here, use a probe array and interrogate the probe array electronically. The only movement left over will then be the simple movement of rotation around this axis. And this will give you much faster measurement than for a fully mechanical system. Some examples of this is in automotive, in which you have electronically scan of the radiation in the probe here. All you have to do is rotate the car on its own axis, and you can map fully the near field radiated by the antenna mounted on the car, and very fast be able to get some indication of the radiation. The same goes for small devices mounted here. Electronic interrogation of the near field sampled by a probe array, rotation of the antenna on the test, and then you have the near field sampling. You apply near field to far field transformation, and you get to the far field. So here is an overview of the different methods. And here you have to be a little bit careful, because I put some of my own conventions in here, and it's not a, let's say, a publicly accepted that the compact test range and the plane wave generators are near field methods. That's my convention. Other people call these for far field methods, because you are essentially measuring in the far field. But as I said before, the compact test range and the plane wave generator are trying to make a far field condition essentially near field. So for me, it is a near field method. The only difference between true near field is that when I do a sampling, digital sampling of the near field, and then digitally I do near field to far field transformation, that's the digital approach. And the compact test range and the plane wave generator, we'll talk about this later, uses an analog approach in which inside, either done by the reflector surface or by the array coefficients, we directly transform to far field without having to apply any transformation. And that's the essential difference between these two methods. We talked about the far field methods, in which you just make sure that you have sufficient distance between the antenna that you are trying to measure and your probe or range antenna. The thing that I have included here is a little bit a very interesting topic that Lucia is going to talk about when I eventually finish my presentation here. It is when we are trying to combine measurement and simulations. And when the measurement problem becomes very big, one of the ways to deal with that is to measure only a part of the problem, which is generally the source. So if you have an antenna that is positioned on a large platform, you can get by just measuring locally the antenna, derive a very good numerical model of that antenna, and then solve the rest, so the scattering, essentially, by numerical methods like the one that was presented by Dr. Reddy before my presentation. So this is going to be what Lucia is going to talk about later when I finish. So let's show some examples. I have a navigational payload that I would like to show you, in which I have some measurements in UHF band and L band. So this is on a satellite. So I have to explain, it's not so easy for me to get my hands on measurement because many of the clients of our systems are protective about this. But the European Space Agency is more generous. So they allowed me to use their measurements so I can show you something to illustrate what we can do in a classical measurement scenario of this example, a satellite. So we have here a Galileo satellite that was produced by OHB, and it was measured in the Hertz range in the Netherlands in Noordwijk. So here, this large antenna here is a navigational antenna. This is a mission antenna for communication. This is a search and rescue antenna, lower frequency, a helix array, and on here we also have the TT&C antenna, all on the upper board of this satellite. So the first measurement that was done was in the Hertz range that we saw before. So you have the satellite here. You can see that the navigation array is actually covered by a thermal protection, but behind here you can see that there will be the patches of the array. And now we are measuring only the TX and the RX antenna at 406 megahertz. So it's actually a fairly low frequency. So the satellite was placed in front of the scanner, and the scanning was done on a more or less 6-meter surface in front of the satellite. And we did both near field to far field transformation using FFT to look at the patterns, but we also did diagnostics using an equivalent current expansion of this satellite. So when we did the expansion using numerical, the electrical currents, we could clearly see that the antenna that is supposed to be radiating is radiating, so that's good. But we also see that there's some spurious radiation coming from the navigational satellite that works at 1.6 gigahertz, so very far away from the 400 megahertz of the antenna that we're trying to measure. So there's clearly some coupling going on. We can see this also on the magnetical currents. So we have both electrical and magnetical currents from the expansion. So this is a post-processing of the measurement that we did in the Hertz range. We can also artificially a little bit take the field contribution and turn them into right-hand circular and left-hand circular currents. So we can see coupling in terms of copolar and crosspolar, and we notice that the coupling is actually stronger in copolar and not so strong in crosspolar. So this is very interesting because normally when you have a scattering problem, your reflection of your copolar is going to be crosspolar, but here we clearly have some other mechanism that in place that is interesting to look at. So what we can also do when we have all these currents here is that we can make a animation of the field. So we can use the currents and then calculate the fields and use a pseudo time domain animation of the currents. So you can see that the radiation from this antenna here is rather good, but here the radiation starts already, the coupling with the navigation antenna starts way before the radiation. So it's a direct coupling and it's not a scattering. So you can see the mechanism. And this is all from post-processing of measurement done on a planar near field scanner of this satellite. So this is very, very interesting to understand what are the coupling mechanisms between these two antennas. And this would allow, or should allow, the engineers in ESTEC to minimize coupling between these two antennas as we'll see in a minute. So what we can see is that we can look also at, we can turn some of the currents on and off, so we can examine what is the real impact of these currents. For instance, we can isolate just the antenna and isolate also just the coupling radiation with the other antennas and try to understand what are their contribution, how bad is it on the final pattern of this antenna. So you can see the color coding here. The coupling is green, measurement is blue, and the antenna by itself, so taking away the coupling, is red. So this antenna pattern was supposed to look like this, but due to the coupling, which is essentially helping copolar, the pattern becomes wider and a little bit more directive. In terms of crosspolar, you can see there's some contribution to the crosspolar here, but the contribution from the crosspolar is essentially similar to what you have in its own crosspolar. So, and you can see this in the two different cuts in phi equal to 90, which is this plane here, and phi equal to 0, which is this plane here. So on both planes, you can see a clear indication of the coupling, but it's mainly copolar coupling. But if this, for instance, this antenna was trying to be used for navigation, then the source coming from two different points would probably create some problems in terms of timing and phase center of the antenna. So generally, this kind of coupling has to be avoided. It's nice to know what are the mechanisms. We also try to measure the smaller antenna here in the center. That's actually at 1544 megahertz. So again, we did a planar scanning of this antenna in the hertz range in STEC. And again, we determined the far-field radiation using standard near-field to far-field transformation tools, but we also try to do some diagnostics using equivalent current expansion on the satellite to understand what is happening. Again, we can see the antenna is radiating almost by itself. There's some coupling to the other antennas, but for instance, the antenna working at the same frequency band, the navigation antenna, is not really coupling with the antenna. So this is a good news. So these are the magnetical currents. So both of the currents show very little coupling between the actual antenna and the navigational antenna on this payload. And also, we can see this in the animation. So again, from the side, you can see that the radiation really has an origin where the antenna is, and there's not much in terms of scattering from other objects. So this antenna works as intended. It doesn't feel the impact of the other antennas. And again, I would like to underline that this is all post-processing of classical near-field, planar near-field antenna measurements. But again, we can look at the currents in terms of right-hand circular polarized currents. They don't exist in free nature, but of course we can do this in post-processing. And you can see that the crosspolar is mainly coming from the coupling with the elements around the actual antenna, but not much is coming from coupling with the navigational antenna. We look at the patterns, and again, the full satellite is blue. Without the navigational payload here, it is red, and just the navigational payload, you can see the coupling is actually really, really small, almost 40 dBs below. So in this case, the two antennas are quite well uncoupled, which is also the intent of when you try to put two antennas on a spacecraft. So it's nice to know. I'm going to show you also some measurement and diagnostics on the navigational antenna. Also, this was measured in the hertz range. It was a prototype basically made by ERDS CASA. This is antenna here. It has 42 stacked patches, and it's supposed to make an isoflux pattern. Isoflux is essentially trying to make the same flux density on the ground, and since we are in a mere orbit, it means that the pattern has a U shape, as you will see in a minute. The antenna works actually at more frequencies from 1.1 to 1.6 gigahertz, and we're going to look at the 1.6 gigahertz measurements on this antenna. So you can see the antenna creates, try to compensate for the larger path length that we have when we look at the ground from a near orbit, and by having this pattern here, so that's wanted. So what you can see is nice is that you have the wanted pattern that from this antenna. You have some higher side lobes that are maybe not intentional, and you'll also notice that the crosspolar is very, very low in this antenna. It's actually a very good engineering feat to be able to get at least a 30 dB crosspolar on axis from an array of patches. When we calculate the equivalent currents on this structure, we can immediately see that there is some coupling with the support structure. So we can diagnose the fact that we had to use a large positioner to hold the array, but the coupling is not strong. And we can, as we have done before, look at the full pattern and also the pattern without the pattern induced, the currents induced on the structure. But you can see the difference is not big. So we can diagnose that the measurement was done well, and there was not a big interference from the positioner on the actual measurement of this antenna. And this was using the spherical near field measurement system in STEC. So before we looked at planar, now we're looking at the spherical near field measurements. What we can see also when we get a little bit closer to the pattern here, we can see some asymmetries in different cuts from the four principal planes, and we can also see it coming a little bit from the equivalent currents, and that it's not completely symmetric, this antenna here, but that's also due to the layout of the array. So the currents, we can, as we did before, we can actually decompose them into right-hand, which is the copolar currents from the array, and we can see pretty clearly the mechanism that we have a center element, and then we use the outer elements in outer phase in order to create the isoflux pattern of this array. What we can do also in post-processing, of course, is we can look only at the inner radiation, which is blue, and we can look also only on the outer radiation, which is red, and plot it here. So the original pattern is this one here, and it consists of the inner pattern here, which is a nice and fairly symmetric pattern, and then not so symmetric outer pattern, as you can see here. It was supposed to lower the radiation on both sides because it's out of phase, and then make the pattern wider. But as you can see, it's not as symmetric, and this is what is causing the asymmetries in the final radiation pattern. What we can do also, out of curiosity, is to isolate different areas of the array, look at the center and three subarrays of this array. All of this is in post-processing from spherical near-field measurements, and you can notice that there is 1 dB, 20-degree difference in the excitation of these subarrays, and this is what is causing the asymmetries that we have in the final radiation of this pattern. The central element, as we've seen, is actually quite good. So what we could also notice is that the 180-degree phase change between the central elements and the outer elements, of course, we have seen it, but we also notice that there's some phase dispersion in the copolar, which is maybe a little bit strange, but it will become clear in a minute what this is from. If we look at the crosspolar, so the left-hand circular polarization, you remember that the pattern in the far field was actually very, very good. There was very, very low crosspolar. But what you see here is that the crosspolar on-axis radiation is only 10, 12 dB below the main peak. And so this is rather curious. How can it happen that you have such a good radiation in the far field on axis when you have at field, let's say, element level, very high crosspolar in the elements? And what we can appreciate is that the phase of the crosspolar changes in groups and therefore cancels out on axis. And this is because the people who actually made this array used what we call sequential rotation. So what they did is they actually rotated sequentially the circular polarized elements and then recompensated the phase. And since that compensation is also not completely working well, this is the reason why we have the phase dispersion even in copolar. But it gives us a boost in terms of eliminating the cross-polar radiation on axis, and therefore we can say that the designers of this antenna have been rather successful in what they did. Let's go and talk about the plane wave generators. So the compact antenna test range, as I said before, in my mind, is a plane wave generator. What it does is that it uses a field that illuminates a reflector that then creates a plane wave situation, so approximates a plane wave situation in what we call the quiet zone. The quiet zone is this area in which we can measure an antenna, because if we put an antenna here, it is exposed to a plane wave and therefore in far field condition. We could also do the same. So this is a single reflector where we have a feed. We could also do the same with a dual reflector system. And if we do some compensation, you will see that the cross-polar we get from such a system is actually rather low. Whereas in a single reflector system, on axis where we have the symmetry axis, we get very low cross-polar. But towards the edges of our quiet zone, we do get a higher component of cross-polar, which is in some cases not so desirable. In other cases, maybe we don't care. But the general way to avoid that is to use two reflectors. That, however, is quite expensive, and therefore we have investigated possibilities to get rid of the cross-polar components towards the edges of the quiet zone. So here is an example of a compact antenna test range in Aachen University. See the reflector here. The feed that is illuminating the reflector is behind this absorber plate here, and the quiet zone is in this area where we have the positioner. That's where we take the antenna and we rotate it around its axis, so we can compute the coupling with the feed and measure the pattern of the antenna directly in far field, because we have a plane wave coming in on this quiet zone here. So looking from the reflector, you can see this is the feed, and this is the reflector antenna that we are testing on the in the quiet zone, as you can see here. And here are some details on a special feed that we designed in order to eliminate the problem with the higher cross-pole in the quiet zone. I will come back to this in a moment. So a typical picture of the cross-polar pattern of the quiet zone is like this. You have a symmetry plane. In this case, since we had the symmetry plane in this dimension here, the higher cross we have in the two planes on this side in our quiet zone. If an antenna like this, and it will clearly be beneficial to put it here for the measurement, because that's where the cross-polar is very low, below 40-45 dBs, and therefore we can measure quite accurately our antenna if we do that. But if we had a case, a small satellite with a reflector antenna, we had to put the reflector here. The actual contribution to the cross-polar from the test range is 10 dB. So our cross-polar that would otherwise be 55 dB turns out to be 40, which is really bad. So what can we do about this? Well, if we use a feed to that, if you put the feed away from the focal point, it would actually radiate fields here and here, and therefore we could use a small field array, these two small feeds here, to cancel the cross-polar components in our quiet zone and make the cross-polar uniform and very, very low in our quiet zone. And thus, when we do the measurement, we don't get exactly what we simulated, which was 55, but we get a 10 dB, at least 10 dB improvement in our measurement of the cross-polar by simply using, rather than just a single feed to eliminate the reflector, we use a small feed array. This can be done in both polarization. So this is a dual polarized cross-polar reduction feed for compact test ranges. Similar, we also use an array to generate a plane wave. This is actually our reflector from before. So we could use an array like this to generate the plane wave condition at the reflector position here. The ones that we make in MVG, but there are others out there, we use a ring concept. So we actually organize the elements in rings, and then we the pattern of these rings in the quiet zone looks like this. And by choosing the coefficient, the complex coefficient correctly of these rings, we can actually generate a quiet zone pattern that is flat. And it emulates completely the arrival of a plane wave in this quiet zone, as you can see here. Such an array can be dual polarized, and actually, since we're using wideband elements, it can also work on a very wide bandwidth. The only thing we have to do is change the coefficient in frequency that are not the same. To illustrate the principle of the plane wave generator, this is a single element. The single element will clearly generate a spherical wavefront, whereas the array, as you can see here, generates a flat plane wave in our test zone, and it's actually quite close proximity to the array. So this illustrates the inner workings of the plane wave generator. Here is some measurements that we have done on the actual quiet zone of the plane wave array. So the plane wave generator is down here, the array. And you can see in a cut at about 1.1 meter distance away from the array, we have a nice quiet zone. This is blown up here. You can see that the variation in amplitude and phase is quite small. So we do generate a plane wave at a very close distance to our array, and we can do direct far-field testing at a very close distance using such technology. So the two plane wave generators, the compact test range and the array plane wave generator, are actually similar in many ways. We use an array to generate a quiet zone pattern, the array, and in the compact test range, we use the reflector to generate the same quiet zone. So the difference is that we use a discrete sampling for the array, and we use a continuous sampling with the compact test and antenna test range. The other difference that we have is that since we can control the coefficients here, we can actually put a taper on our array excitation. So we don't get a hard truncation of the field here. So we get less ripple in our quiet zone. Then in the compact test range, the problem is that the feed is illuminating the reflector. So we really cannot control the amplitude so well. So we need to have an edge treatment in order to create artificially this effect so that the quiet zone field can be nice. In any case, it's not impossible to make a good test range. I mean, it is, after all, one of the normal, let's say, the very common test ways to test antennas since about 40 years.
Yes, Mr. Lars, sorry,
yes?
Sorry to interrupt. How much time would you take for this?
Let's see. I think I actually have finished. I just want to show you an implementation at the millimeter wave at the same concept. So when we're testing a live person using a plane wave generator, so that this is actually quite important for people who are making 5G phones, that you can test the shadowing that you will have from a human head in talk position, and to choose between the different antennas that you will have in your 5G phones. This is one of the applications that we are looking at millimeter waves for plane wave generators. And so now I'm actually finished. So the conclusions is that we have looked at some different techniques, far-field techniques. Generally will measure the performance in a single direction, but it will do that instantaneously, so you get an idea about the coupling instantaneously. Near-field techniques require sampling over generally a closed surface, or at least a large surface, so they take a little bit more time. The far-field systems can be plane wave generators. That could be compact test range or the array-based plane wave generator we've shown. Near-field antenna measurements are generally considered to be the most accurate measurement technique. It can be sometimes be maybe a discussion point, but it is more or less considered the very accurate. But if you have a far-field system that is well designed, that is of course also very, very accurate. Near-field techniques require near-field to far-field transformation. What we're going to look at now with the Lucia is that from the near field to fiber transformation, when you do expand, also using, for instance, equivalent currents, then you have an access to a wide range of diagnostic tools. And I showed this in different scenarios on a satellite, but it's also a possibility to provide a link between measurement and numerical simulation tools. And this is really the introduction to the presentation by Lucia in a few minutes. If you want to know more about this, it's good to go and look at the IEEE standards. You go check out this book. It's one of the Bible of antenna near-field measurements. If you want to know a little bit more about modulated scattering and the multi-probe systems that I showed, then this is a really good book. If you want to know more about the post-processing techniques that I illustrated, then this is a book that I managed to write last year that is now out. It contains what I talked about today and a lot more. And that is ended. Thank you very much. Sorry that I ran a little bit late.
No, sorry. Thank you, Dr. Lars. There are a couple of questions, but I'm thinking, can we take the questions after Lucia's talk?
Yes, definitely we can.
Okay. Thank you. Thank you so much. And may I introduce the next speaker? The next speaker is Ms. Lucia Scialacqua, who received her MS degree in telecommunication engineering from University of Siena, Italy in 2006. She was a student under the Erasmus program, Denmark Technical University Lyngby, where she developed her master's thesis on design of reference probes for near-field antenna measurements in 2006. In 2007, she joined the MVG, formerly Satimo, as an antenna engineer. In MVG, she worked initially as antenna engineer for designing, testing, and reference antennas and custom radiators under customer specifications. Then she's currently the scientific software department engineer, being technical responsible of the MPG software Insight for measurement and antenna post-processing, which uses the equivalent current reconstruction for antenna diagnostics and linked with commercial numerical tools. She has authored or co-authored over 80 journal and conference papers on antenna design and measurement techniques and 2 white papers. She has contributed to 1 book. She was a speaker for 3 webinars on measurement antenna for post-processing based on the equivalent current technique. And thank you so much. May I ask Ms. Lucia to proceed with the presentation?
To everybody, can you hear me well?
Yes, we can.
Okay, perfect. Let me share my screen. The presentation. So, can you see my screen very well?
Not
yet.
yet.
Not yet.
Okay, just 1 minute, sorry. Let me try again.
Perfect.
Okay, perfect.
Yes, perfect. Thank you.
I hope that is in its full screen.
Yes.
Okay, perfect. So thank you for the introduction. The presentation that I'm going to start will show the synergic use of antenna measurement and numerical simulation in antenna placement scenario. So the presentation is structured as follows, and the presentation has been prepared in collaboration with Altair. And so we will start with an introduction and motivation. Then we will describe the workflow of the link between the measurement and the simulations. And then I will skip to the preparation of the near field source by Insight, and the example will be based on a monochrome antenna. And finally, we will use this measure source for a simulation in Altair FICO using 2 examples. Let me proceed with the first part, the introduction and the motivation. So the electromagnetic analysis in complex scenarios require the domain decomposition technique. This widely occurs for antenna placement problems, and in all the applications, the overall accuracy of the simulation is linked to the accuracy of the radiator representation. High-fidelity results can be reached in case the electromagnetic model of the antenna is available. But if this is not always possible, because the antenna manufacturer are reluctant to share this model because they would like to protect the intellectual property rights of these models. And instead, the antenna integrators need to these models to set and to predict the performance of these radiators in the large platforms, such as aircraft, vehicles, ships, and satellites. In order to overcome this limitation, we can use the link between the measurement and the simulation. Whether the electromagnetic models are not available, or in case of on-shelf antennas, we can use different approaches. First of all, we can create the CAD model or an equivalent or similar antenna. The second approach is to create an equivalent source starting from the measurement of the radiators, and then we can import the source, the measured source, in the simulation tool. And this is what the main topic of this presentation. The third approach is based on the full measurements. Linking the measurement and the simulation means creating the effective link between these two data sets. And this approach is convenient and is really powerful when, for example, no CAD model is available or we have only the simulated model. The link between measurement and simulation is also a very powerful approach when instead the measurement, the full measurement of such a large platform is not available. In case such system, like that one that is here depicted, is not possible to be used. Thus, the link between the measurement simulation is the only approach that allows to use the real antenna, so not the simulated one, and it allows to measure the antenna in a smaller measurement system anyway, and to include the real representation of the antenna. To make a summary of the benefits of the link between measurement and simulation allows to share antenna data without exposing proprietary data. It allows to have an high-fidelity representation of the radiator for an accurate characterization of the final scenario. It allows to represent the physical antenna, so real materials, real feeding conditions, and real mechanical design. And we can solve with this approach very enormous problems or realistic problems that otherwise cannot be fully simulated or fully measured. In this slide, I would like to show you the link between the MVG measurement systems, so the MVG measurements, and the set of all the simulation tools that are compatible with the MVG measurements. The characterization and the post-processing of the measured data in terms of near-field source or in form of Huygens box is done by the software inside that I will describe in the next slide. Let's keep to the first part of this technical session that is dedicated to the workflow of the link. The link is composed by 3 steps. The first one is the measurement of the radiators. The second one is the preparation of the near-field source from the radiation pattern, while the third one is the simulation of the near-field source in the final scenario. In this example, we have used a shark fin antenna that has been measured, post-processed, and installed on this car model. Let me start with the first step of the workflow, that is the measurement of the radiation pattern. Usually, it is convenient to use the near-field data when the near field is available. But in case, because the near field contains more electromagnetic information, but if, for example, the far field is not available, anyway, the far field the far field is available. We can anyway use the far field, and we can anyway compute an accurate near field source. I would like here to focus only on the multiprobe technology, since Lars already largely explained the near field and far field measurement techniques in the previous presentation. And here I would like to mention the multiprobe technology, that is the technology used by the systems that are applied to measure the antennas that are here presented. And so in the multiprobe technology, the elevation scan is performed via probe array electronically, while the mechanical scan is the azimuth scan and is performed via turntable. The possibility to perform an electronically scan via probe array allows to reduce drastically the measurement time, and for example, for an antenna under test of diameter less than 10 wavelength for more than 20 frequency points, we can perform a measurement, for example, only in a few minutes. This is an overview, just to give you some example of the multiprobe systems that MVG can provide. And the overview of the systems goes from 70 megahertz to 50 gigahertz, so also for 5G applications. And the different dimensions and design of the arch and of the system allows to cover the different frequency bands and to test the different applications. And we go to the step 2 of the workflow that is dedicated to the preparation of the near field source. The near field source is prepared by the software Insight, and that implements the equivalent current method. That is the numerical method able to transform the radiation pattern in terms of near field box that is then imported in the simulation tool. Insight, starting from near field or far field pattern, allows to compute the equivalent current on a three-dimensional surface that is conformal to the test object. And here an example is depicted in this slide of a horn that has been measured in the StarLab measurement system. Here we have an example of radiation pattern, and defining this three-dimensional geometry, Insight is able to reconstruct the electric and the magnetic current distribution on this such detailed geometry. As you can see, we can get very important information, detailed information on the design and on the current of this antenna. And this information is mainly used for diagnostics. The more detailed geometry, the more diagnostics is available. When instead we need to use Insight to exchange the measured data with the simulation tool, we don't need to use such detailed geometry, but a box has been already validated as an accurate geometry that is able to perform an accurate link. And the box has been selected since it's the most simple geometry compatible with all the commercial electromagnetic tools. But let's go to discover the origin of the numerical method able to create this measured near field source. The inverse source method, also called as equivalent current method implemented in Insight, is rigorously based on the application of the equivalence theorem. This allows to substitute the antenna under test by a closed surface falling close in the antenna where the equivalent current are placed, and this surface is denoted by sigma r. The currents are imposed to radiate the field that is measured, and it can be acquired by the surface, that is the measurement surface, scan surface, that is denoted by sigma m. The system of equation is discretized by the method of moment in terms of raw Wilson-Glisson Basing function, and the condition of internal field equal to 0 guarantees the uniqueness of the system solution. The equivalent current method can be applied to process any measurement data. So we can start from near-field data on different scan ranges, for example, spherical, cylindrical, or planar, or even far-field data. And here an example of a passive slot array operating in X-band is depicted. And we can see how, starting from different near-field data sets, we can efficiently reconstruct on the same geometry the same or comparable distribution of the equivalent currents representing the antenna. And this shows the efficiency of the method starting from different near-field scan ranges. And we arrive to the step number 3 of the procedure that consists of simulating this near-field source in the final scenario. And I will show you in the last part of this presentation how we can apply this near-field source data in the tool AlterFICO. Now we start with the part dedicated to the preparation of the near-field source. For this presentation, we have selected a monochrome antenna. This is a reference antenna by MVG that is that works from 2.2 gigahertz to 6 gigahertz. And here, in particular, two tested frequencies have been selected: 3.3 gigahertz and 5.28 gigahertz. This is the model of the monochrome antenna. And here we have just an example of the placement of this antenna on a rectangular plate. This antenna is a flush-mounted antenna, so this is not a simple detached antenna. And in case of flush-mounted antenna, we have a more specific procedure that is typical of these such radiators. In fact, with respect to the detached antenna, for flush-mounted antenna, the scattering, the proximity of the scatterings of the structure modify the behavior and the performance of the antenna itself. And the ideal condition is to have an infinite ground plane boundary condition. That is the best approximation that we can have. But in reality, this is not possible to realize it. So what we can do? We can just emulate this condition by measuring the radiators on a finite ground plane, on a circular finite ground plane, and then we apply a post-processing of this measurement in order to reduce, to eliminate the diffractive contribution from the edge of this plate. And in this case, we are going to restore this infinite plane boundary condition. In order to perform a measurement that is accurate for this procedure, we suggest to use a circular ground plane of diameter at least 2 wavelengths at the lower frequency limit of the frequency point of the frequency band. And in this case, the dimension of the ground plane is 7 wavelengths at 5.28 gigahertz. So this condition is largely satisfied. After post-processing, after restoring this infinite ground plane condition, we can just reconstruct and compute the equivalent current only on a box that includes the antenna only. And this is an example of this box. This is what we represent here in red color. It should be noted that since an infinite ground plane condition is considered, the image of the source antenna is initially included in the equivalent current computation, and then it is removed when determining the Huygens box representation of the measured source. This is the whole workflow of the link. So, first of all, we measure the radiator on a finite ground plane. This is the near-field radiation pattern that is correspondent to the radiator on the circular ground plane. As you can see, we have the ripple that comes from the diffractive effect from the plane. Then we apply the infinite plane boundary condition, and this is the pattern that we obtain. And finally, we can just reconstruct the current on the box, enclosing the antenna only. This representation is accurate and has been validated as general to be applied and to be positioned, this source, on a generic surface or platform. In this case, we have placed this box in the rectangular plate in the original position of the setup that I showed you just at the beginning. So now we have post-process the radiation pattern, we have the measured source, and we can proceed to import this measured source in FICO for simulation in different scenarios. So, as CJ Reddy presented in the first presentation of this afternoon session, FICO is a three-dimensional comprehensive electromagnetic simulation tool that is able to solve a wide range of electromagnetic problems. FICO is also able to import and manage near-field source by InSight. We will use FICO to predict the performance of the monocone antenna for two examples. The first one is the rectangular plate that I showed you before, and then we will include and simulate the monocone on a more complex platform consisting of a rotorcraft model. Let's start with the first application, that is the monocone on the rectangular plate. The monocone has been positioned in a offset position location, as you can see from this picture in the measurement setup. And here the frequency band, the dimension of the plate and the position of the monocone is reported. And we have simulated, we have performed the full wave simulation of the monocone on the rectangular plate, and also the simulation with equivalent sources that I showed you in the previous procedure. We have also performed the measurement of this scenario, so the antenna and the plate in the Starlab measurement system, in order to have a reference data set, because the aim of this example is to make a validation of the procedure, also comparing simulation with measurements, with full measurements. Initially, we perform a simulation, a full wave simulation, to check the performance of the monocone when it's installed on this platform. And we can say, observing the return loss, the matching, that the presence of the platform does not affect so much the performance of the antenna. And also the distribution of the instantaneous currents is reasonable for at all the frequency points. So this confirms that the setting of the simulation is well done and the simulation is accurate. Then we can proceed in importing the measured source in FICO. This is done by a procedure based on two steps. The first one is the import of the measure equivalent source file into CAD-FICO. And this feature is accessible in CAD-FICO, going to field current data, then import near field data from file, and this dialog box will appear. We can select the option Orbit SETIMO and browse the measurement file. In case the measurement file contains more than one frequency, the block number can be used to index the frequency. Then we proceed to the second step, that consists of creating the equivalent source in FICO, and then to associate the near field before imported to this equivalent source. And this is the procedure is just depicted in this slide. And then after associating this near field to the equivalent source, we can even position the source in a specific location in the working plane. Now we proceed to show the results. Here we have the first comparison in terms of radiation pattern. And this is the gain radiation pattern between the full simulation, that is the FICO simulation with the monocone antenna, the simulation with the measurement equivalent source, that is the link between the measurement and the simulation, and the reference measurements. We show here the first frequency point, so 3.3 gigahertz, and this is the cut plane elevation cut phi equal to 0 degree that is along the longer side of this rectangular plate. And we can see that the agreement is really good. Now I would like to show you the other cut plane that is along the shorter side of the rectangular plate. And we can see that the agreement between the two data sets by simulation is excellent. And this shows also the validity of the approach. We have some small discrepancy between the simulated data and the measurements, but this comes from the presence of the mounting support in the measurement setup, in the real measurement setup, that is not taken into account in the simulation. And this is more evident on this cut plane because here the side of the rectangular plate is shorter. Now I would like to show you the results for the other frequency point, 5.28 gigahertz. This is again the cut plane phi equal to 0, so this cut plane. And we can see that the agreement is really good with some discrepancy with respect to the measurement that is for the reasons that I already explained. And then this is the agreement on the other cut plane. Here we can see that the agreement between the measurement and simulation is better because since the antenna is more directive, we have that the influence of the mounting support is less evident with respect to the other frequency points. So these very good agreements between the three data sets show how this approach is so efficient. And so using the measured sources with the real representation and the real materials, real mechanical design of the radiator allows anyway to obtain very accurate results, really comparable with the full wave measurements and with the full wave simulation. And now we proceed with the other example. So we have placed the monocone antenna, so the measured source, on a rotorcraft model. In FICO, there is a comprehensive component library that allows users to select different antenna types, as you can see here on the list, but also some platform. And for example, here we have a car and an helicopter. That is the example that we'll use in this presentation. And after selecting an antenna or a platform, the user just clicking on Add to Model can import this platform in CAD-FICO and start to work on it. The monocone antenna in this example has been placed in different locations. Here, the dimensions of the aircraft and also in terms of wavelength at 3.3 gigahertz, so the working frequency is reported. The monocone will be placed in front of the fuselage, on top of the rotor, and in back of the fuselage, as here is reported. The aim of this example is to illustrate the feasibility of the link between measurement and simulation when, for example, a full measurement is not possible, because in this case, this aircraft is so big for a measurement system that since could be really, really large, could be not available for such tests. So in case we cannot measure the full aircraft, anyway, we can use the link, including at least the real representation of the antenna with respect to having only the simulated model, or in case the simulated model is not available.
Hello, Lucia. Just reminding you of the time, please.
Yeah, go very fast. Okay. I would like to show you the results for the first position in front of the fuselage. So here, I would like just to show you the agreement between the simulation with the monocone antenna and the full wave simulation. As you can see, the agreement is excellent, and this is the cut plane oriented on with respect to the aircraft, like here is depicted. And let me show you also the other cut plane that is stayed along the longer dimension of the aircraft. As you can see, even the radiation pattern is really complex. The agreement is excellent. Let me show you briefly also the other position. So here the antenna has been placed on the top of the rotor. Again, this is the agreement on this cut plane. As you can see, the agreement is excellent on phi equal to 0, and also for phi equal to 90 degrees. Finally, let me show you the last position in the back of the fuselage. And we can see that even in this case, the agreement is excellent. And if you consider that this is a complex trend of the radiation pattern, this is really impressive, these results. So to make a summary and to go to summary and conclusion, the motivation of combining measurement and simulation antenna application has been introduced, focusing on advantages of the link with the simulation tool. We have presented a workflow focusing on the measurement process, the preparation of the near-field source, and the simulation in FICO. We have prepared a near-field source based on a monocone antenna that then has been demonstrated and simulated in FICO for different applications, a rectangular plate and a rotorcraft model. And this approach is very powerful and so convenient when the electromagnetic model is unknown or not available, since it allows to overcome this limitation and to predict accurately the performance of the antenna, even in complex scenarios. Thank you for your attention, and in case you have questions or you would like to have more information, do not hesitate to contact us by this email address.
Thank you very much, Ms. Lucia. So we may take a couple of combined questions for these sessions addressed to Mr. Lars and Ms. Lucia.
Yeah.
The questions are there in the chat box. Just give me a moment. Yes, there's a question from Dr. C.J. Reddy. Dr. C.J. Reddy and Dr. Sudhakar Rao and everybody has commented for the excellent talks that both of you have provided. And the question from Dr. Reddy is, for the plane wave generator, what are the typical antenna elements used? Are they Vivaldi type elements? I think this is addressed to Mr. Lars.
Yes, that's a good question. Let's say at lower frequency, so below 6 gigahertz, which is let's say the cutting frequency for, let's say, many applications in personal communication. Generally, it's Vivaldi type antennas. Also due to the fact that you need a large bandwidth and you need to minimize the elements so that you can fit them together quite densely. So that's the general, the preferred element. Now there was another question also about for the millimeter wave. It's true, it's a good observation that normally you would use a corrugated horn. What is not visible is that we are using a shaped flare inside the horn. So the horn is not just, let's say, continuously increasing, but it actually has a very complex shape that works a lot like corrugation and take care of the crosspolar.
Yeah, thank you very much, Mr. Lars. Thank you, both of you, for the excellent talk. I think it's time to go to the next session for the panel discussions. And may I hand over the podium to Dr. Shah.
Thank you.
Thank you very much, Dr. Siddiqui, for moderating this particular session. And also to the speakers of the evening session, starting with Dr. Reddy, and then Lars and Lucia for excellent presentation. So I believe the audience are definitely encouraged, and they will get some impetus, and they will probably write to you also on some of the things, because due to the time constraint, we couldn't have a prolonged interaction. So now we are moving to the next and the final session of this 2-day-long workshop. We named this as IEEE Space Antenna Workshop, ISAW-2020. This year we increased the horizon a little bit, and the title is Advanced Antennas for Space and Industrial Applications. So I saw the name when we started in 2018. It was something like the last event of the year. So you have seen all the events of across the globe, starting from APS to some of the Indian conferences, and then you conclude the year with this Space Antenna Workshop. So that was a very unique name. It emerged. So we will start the panel discussion now. The panel members we have here are all the speakers. Then we have Professor Yahya Antar, who has already joined. Good morning, sir. And then we have we have Professor C.K. Anandan and Dr. Poddar. I think he's there. Dr. Poddar, are you there? Yeah, maybe he will be joining us soon. So directly, without taking much time, I'll be going into the theme of the panel. I would request Professor Yahya Antar to make some introductory comments regarding the opportunities and challenges for students and young professionals in antenna and industry and academia. Over to you, sir.
Thank you very much, Chinmoy. This has been wonderful. I really thank the speakers and the attendees for their, for their wonderful talks and wonderful discussion. Thank you, all the organizers, for this. And I think we are in a good shape. We have challenges. We have lots of things to do, and I encourage you all to get involved and move on. So let us start the panel discussion, and let us hear from the speakers, and let's hear from the audience and the young students, and let's have a discussion. And I hope this will continue in other forms as we move on. So, thank you.
Thank you very much, sir, for your introductory comments. So before we take the podium to the open forum and asking some of the scholars, PhD scholars, MTech students, and young professionals to ask your question, I'll hand over the podium to Dr. Rao, who wants to have some introductory remarks. Dr. Rao, please.
Thank you, Chinmoy. I think this is probably one of the best workshops in recent years. I think I mentioned that before. And thanks to all the speakers for excellent presentation. And thanks to all the students and participants. I think this is a good opportunity for the students, I think, to get trained and understand the basics and what are the things happening in the industry, either space or defense or wireless or any other industry. I think the workshop actually covered all the topics: antenna designs, simulations, measurements, aircraft designs, FSS, a lot of topics I think covered. I think it's a bit